Okay, let's come back. So because actually I have finished the content for week 10 already, but I would like to start the content for week 11. That means the diffusion model a bit earlier. I will not cover the whole stuff today, don't worry. So I will just cover a few slides from the week 11 diffusion models content. So because the notes I prepared for week 11 is very probably a little bit more than I expected. So in order to make a better use of time, I will start the diffusion model today, and but only a small portion of it. So I will continue the diffusion model next week, but I will start now so that I will not be so constrained by time next week. Okay, so so far, let me just put this. So far, we have in this course we have been talking a lot using the deep learning, different kind of deep learning model to 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 apply on image and video on the recognition side of application, like the classifications we have just covered on the video classification, image classifications, and as well as image segmentation we have been talking about previously. And we haven't talked about the generative side of the image applications using deep learning. And it is probably one of the breakthrough because we haven't in the old days in computer visions or AI, they don't know how actually they don't really observe how to create content, create image. And the generative AI started, I would say it started from the linguistic because of the success of transformer applying in the linguistic applications. They can they're not just only understand the text, but also generate the text. And that is probably the begin. And in the image side, there has been in the traditional computer visions, it's only focusing on recognitions or understanding. But the generation of visual content or image or video, they are not done in computer vision. They're actually done in a separate area called computer graphics. I think I hope you have heard about that. Computer graphics. And in computer graphics, it is a very old area. It started from 1960s, where we have the goal trying to use the computer to draw a picture as real as possible in the old days, and it has been so successful, and it has been they use the in the traditional way in computer graphics is to use physics simulations to simulate how the light is transport in the space. Okay, so like ray tracing, like radiosity, all these techniques. Don't worry about the terminology if you don't understand. It doesn't matter. I just want to tell you these technologies are based on physics to synthesize image, and it has been so successful that you see the result in the movies like Toy Story, like all the like Godzilla, Star Wars. They has been used in the latest Star Wars movies. A lot of them, a lot of sci-fi movie, they are using them, using the technology from computer graphics. And as well as one of the most important application you have been using every day is computer games. Okay, I think even you don't play game too much, you know what is computer games, and they are based on the techniques developed on the computer graphics for generating. And again, one of the most important development throughout the time from computer graphics is GPU, stand for graphics processing unit. And from the name, you can tell is originally designed for graphics, designed for drawing pictures. Okay. And but this also helps AI. Without GPU, AI doesn't work because of the computation is so big. You need a parallel machine in order to do it. And GPU was so successful because, to be honest, many years ago, people use there are parallel machine designed like MPP designed for AI, but it doesn't work out because it's too expensive. The development of GPU is so important to AI because it's a commodity or consumer level parallel computing. So that means it is very cost effective. You don't need a very expensive budget to buy hardware for your AI. You can just use those designed, specially designed for graphics purpose and use that for AI. Without the GPU, we don't have today's AI, I can say. Okay, then what? Now the history come back. So it turns out we now have a very powerful and practical AI. And it turns out maybe we can use that not just for recognitions, but also for generations. An example like I have said about for LLM, for image. So we're focusing on image and video generations. So there has been several techniques proposed. One of them is the generative adversarial network, GAN. I think even unfortunately this course we don't cover it anymore. I think you have learned it from other learning course. This one give you pretty good result, but unfortunately it is unstable to train, and it's sometimes very hard to train. So whenever it's unstable to train, you cannot scale up. Today's we have those large data trained AI model for image generation, video generations. They rely on training on tons of data, and you need to scale up in order to. You need to be stable to train. Otherwise, if let's say you spend thousands of hours on training and then you crash, and there's no way to get the result, but you lost a lot of money from training. So GAN is not a good idea for large scale data training because it's unstable to train. Another approach for generating image is the variational autoencoder. It has been used for a while, but usually it has a problem is over smoothing. The data is not that good in quality, unfortunately. And so it's also not usually used. It turns out people now are more satisfied with this called diffusion model. Okay. And it has been used in image as well as video generations. A successful case like what? Like Midjourney. So it's a company doing image generations and let the consumer to subscribe to the service so that they can generate image. And there are also like other example like Sora. I think Sora is less successful, to be honest. And there are video one, but Sora is one that first demonstrate the possibility to generate the video using diffusion model. So these are the successful case, and there are many. So actually, it became so. For those of you who are interested, you should take a look at one of the community because this Comfy UI community, Comfy UI is just a UI. To be honest, it integrate a lot of those models together so that people can use them for generating different kind of visual effect. So for those of you can take a look, I think in the Reddit they have they have a chat room for that. I don't know. Okay, so so let's take a look at what is diffusion model. So diffusion model is so the base of diffusion model is not a deep learning. It is actually a formulations of two process. One is forward and the other is backward. Okay, or sometimes called reverse. uh, sometimes we call reverse. Okay, it doesn't matter. And the reverse is, I will talk about that in the next slides. So what is that? What is forward diffusion? So the idea is like this. So let's say I have an image, and then I would do a diffusion process. What does that mean? What is the diffusion process? Is that we will gradually adding noise. That's my pen for here. We're gradually adding some noise into it slowly. Okay, like this. We add a little bit of noise of it. So you can still see this cat, but it's a little bit noisy. If you continuously adding more noise into it, like this, eventually you will get a noise map, completely noisy, and you see nothing about a cat. So this is called diffusions. Okay, I just tell you the mechanism, the formulations here. And this is we call the forward diffusion. We define it called forward diffusions. Okay, so it's not very interesting. We just corrupt everything. The more interesting part about diffusion model or diffusion formulations is the reverse process. What does that mean? Because we know at the end we got a noise image. If we can take away the noise gradually, maybe we can get a clear image. Okay, we can slowly remove the noise and hope that we can get a clear image. Okay, so here I didn't say we can get back the original image. Usually you cannot get back the original cat. You will get something, if you train properly about this, you will get something similar to a cat. Okay, so but don't worry about the training first. Just look at this mechanism. The mechanism is the reverse process. We just gradually take away the noise and a denoising process, and it's reversed. And this process is actually generative because each time we would deduct some of the noise, remove some of the noise, and of course, this noise uh, is stochastic. Okay, it's not deterministic. Okay, so let's formulate this as a statistical process. So as we said, each time we start from a one previous image, add a little bit amount of Gaussian noise to it, we get a new image. So you can formulate this as the equation like this. So it's actually a distributions of the data xt, the distribution of xt given the previous image, previous clear image. The distribution of xt is actually a Gaussian, is a normal distributions because it's basically having a mean. This is the mean of the, which is the previous image scaled. It's a scaled down versions, something like a scaled down the versions of the previous image. Okay, and you add some noise to it. So this is a normal distributions. You can describe the next image. The next image is the normal distribution of the previous image. So this is the forward one, which means you can also determine every one of them, let's say this guy or this guy, by starting from x0 because it's like a Markovian. It's a based on every one is based on the previous one. It's like a Markovian chain, and so you can write that into a sequence of Gaussian process, and that means you can jump from x0 to the target noisy image x4. Okay, like this one. And to simplify the notation, what we want to do is that let's simplify this. We don't like this guy is too long. So we simplify them as this. We simplify the notation. And then every one of xt, every one of them, every one of them can be written given the condition of x0, we can write them. And because the sequence of process is Gaussian, if you remember, this guy is Gaussian, and the final one is also a Gaussian. It's also in this normal distributions. Okay, and it's a normal distributions with a mean of the x0 multiplied by a scaling factor, adding a sequence of noise over here. So a particular image xt can be written as the starting clear image with some scaling and another scaling of the noise, because you are adding noise gradually. Okay, so depending on where is this t, where is this particular t, you have different ratio of the scale down versions of x0 and the scale up versions of the random noise. Okay. So here are some technical one. So this beta we usually call the schedule. So you determine how this noise will be added. Okay. So now I just want to show you the pictorial explanation here. So let's say this is the cat image. So you have a lot of different cat image, okay? Not just one cat. You have another cat 2, cat 3. So all this cat image form a distribution. So this diagram is actually a distribution of all the different kind of cat image. Maybe some cat is sitting there, some cat is standing there, some brown cat, some white cat or black cat, whatever. So you have a huge number of cat image. So their distribution populate something very irregular like this one. And then, so what exactly is this forward process? This forward diffusion is actually adding noise. Remember here, the difference between these two is you add a Gaussian noise. Okay, so gradually you add some noise into it. And if you look at the equations, look at this one. This one is clear. So it's just like the original image, original cat distributions, scaling down, and then you add more noise into it. And this noise, as I said, is a Gaussian noise. It's a Gaussian distributions noise. So effectively, you are blurring your image gradually until it turns into a normal distribution. Okay? And mathematically, you can prove that by taking the distribution of your cat images. And this is just a truth. So you can just, for X, is a joint distribution between any particular cat image is sum over all the case. And that is the particular, let's say this guy, particular this XT, the distribution of this XT. And then you can further derive that. This is just the statistical equations. You can extract this guy out and turn this joint distribution into a conditional one like this. And this one is the input data distribution, your cat, for example. And this one is the diffusion kernel, which is, if you still remember, diffusion kernel, this guy is a Gaussian distribution. And that's it. Which means this is a Gaussian distribution. This guy is something else, something like this. So as you move along the T, move toward the noisy side, you just have more portions of the Gaussian shape, and until you turn into a Gaussian. Okay, that's it. This is forward. Then what? Then the most interesting side is we know that this is a Gaussian. This is a noise, normal distribution, a noise. And the reverse process is, you can say, is a denoising process. Let's say it's going this way, taking away some of the noise, removing some of the noise until hopefully we can get some cat image. Okay. So what is that? If we can do that, let's say assume we can do that. We can just take one in practice, what we can do. That means we can take a Gaussian map. This is a Gaussian map. We sample one of them, get the xt that is here, any point over here, any particular Gaussian noise map, one specific case. And then we will do what? Each time we will remove some of the noise, okay? And we know that to get the next clear image, so start from xt, we want to get xt minus 1, okay? And we know the distributions of this particular less noisy image having a form like this. It basically is just giving the xt, what is the distribution of xt minus 1? There's nothing, okay? Unfortunately, this looks familiar, but it's not the same. We know exactly what this will look like in the previous one, like this one. We know exactly like this. That means xt given xt minus 1. But during the process, this guy is different. Pay attention on this because it's a reverse process. They are different. So these two are not the same. Okay. And unfortunately, we even don't know what is this. What exactly is this? Okay, we don't know. But we can approximate. We can approximate this guy as a Gaussian. So basically, you can say we assume this is a Gaussian. Okay. We assume this guy is a Gaussian. And if it's a Gaussian, all we need to do is that we need to know that very few parameters to learn. How high is this? How wide is this? Right? We can tell a Gaussian distribution if you know this. So the idea is if we assume the reverse process, the adding the noise, even we don't know what exactly it is, we assume it's a Gaussian. And if it's a Gaussian, we can estimate the parameters. We can predict the parameters or estimate it using what? Let's say this is the distribution of the xt. We can assume this is a Gaussian. So if you know this is a Gaussian. And of course, we don't know what are this. We don't know what are this. But we can assume we can train. We can train it using a neural network. Okay, if we can train that, we can do the denoising. So that's the whole idea. So today what I want to say is that the diffusion process is actually a forward fusion and a reverse denoising process. There are only two processes here, and this formulation is a statistical formulations. There's nothing to do with the learning at this moment. The learning appear only after we assume the noise is a Gaussian noise. We can remove that noise, which is Gaussian distributions. Only after this assumptions, maybe we can use a neural network to train and estimate the parameters of the Gaussian distributions in order to let us get or generate clear cat. Okay. But I can tell you, usually it is not, first of all, it's not a reconstruction process. You cannot get back the original cat you use for training. but you will get something very similar to a CAM. Okay. So I will stop here. I know that you need some time to digest the meaning of here. So go back, have a look on the slide. So all the slides of week 11 has been available online from the Moodle. You can download it. And I will put the video for this part of the lecture under the week 11. So you can go back to look at it after I have cut and paste the video because I need to chop this video into two parts. And so you can have a look at home. So I will stop here because it's right time to stop and I have finished what I want to talk today. So if you have any questions, just feel free to stay and ask. If you have no questions, I will see you next week and also during the apply sessions. Thank you very much.